This is section 2.4 called Acids and Bases. In this section, we will define what an acid and a base is. We will also learn how to name them.
There are several definitions of an acid. Arrhenius defines an acid as a substance that produces hydrogen ions when dissolved in water. If we take a look at this formula right here, HCl, you will notice that when it is dissolved in water, it breaks apart into the hydrogen and the chloride ion. Immediately, that hydrogen ion reacts with water to form the hydronium ion, as seen in this picture right here. That hydronium ion represents an acid. How do we identify an acid? Well, we're going to be looking for a covalent compound, one that is made up of only nonmetals, and a hydrogen sitting in the first position of the compound. Notice that each one of these examples down here has a hydrogen sitting in front. It doesn't matter how many hydrogens are sitting in front. To name a binary acid, which is a non-oxygen acid, we first have to identify one. These compounds will start with hydrogen. They will not contain oxygen, but will contain some other nonmetal. To name these, you're going to use the prefix hydro and the suffix ic, and sandwiched in between those, you will put the root of the nonmetal that is in the chemical formula. There are 3 examples of binary acids on this chart. If we go to the far right, you will see that each one begins with the prefix hydro, ends with the suffix ic, and sandwiched in between are the root of the nonmetal that is found in the chemical formula. It does not matter how many hydrogen ions are in the formula when naming a binary acid. Example 1 is a binary acid. I see 2 elements. One is hydrogen, and the other is a nonmetal that is not oxygen, called bromine. So binary acids are named by using the prefix hydro. We're going to take the root of the nonmetal, which is brome, and we're going to add the suffix ic and the word acid after that. We also have oxyacids. Oxyacids are compounds that contain hydrogen. They also contain an oxygen and some other nonmetal. The combination of the oxygen and the nonmetal actually make a polyatomic ion. To name an acid that has a polyatomic ion in it, we will use either the suffix ic or us, depending on if the polyatomic ion ended in ate or ite. We do not use the prefix hydro when naming an oxyacid. If we look at this chart of oxyacids or ternary acids, we're going to focus in on these 2 examples. Now I see that there is a hydrogen, a nonmetal, and a certain number of oxygens. In the first example, I can recognize that ClO3 is chlorate and ClO2 is chlorite. So recognizing that this is an oxyacid, what I'm going to do is I'm going to cross out the suffix and I'm going to replace it with ic, and I end up getting chloric acid. For the second example, since it ends in ite, I'm going to replace that with the us ending, and this time I get chlorous acid. If I take a look at the top 2 examples, we're going to do the same thing. First thing I notice is that is called sulfate, and this is called sulfite. We're going to drop the ate ending, and we're going to replace it with ic. The only difference here is, and this is particular to sulfur, we keep the entire word instead of just a portion, like down in chlorine. So this is sulfuric acid, and this is sulfurous acid. Example 2 shows us an oxyacid. I've got my hydrogen, and the nonmetal and oxygen make up the polyatomic ion, which we can look up on our reference sheet, which is called nitrite. So to name this, I'm going to drop the ending and replace it with us, and then just add the word acid. Remember, no prefix of hydro will be found in the name of an oxyacid. Example 3 is also an oxyacid. I have my hydrogen, and this time I have the polyatomic ion acetate. I'm going to drop the ending, and I'm going to replace it this time with ic, and then I'm going to add the word acid, acetic acid. So this is your self-check. Go ahead and try to name the following 3 acids on the slide. Go to the next one to find the answers. So the first 2 are both binary compounds. They both have a hydrogen and one other nonmetal that is not oxygen. And so you'll notice that they are named with the prefix hydro and ic, and the root of the nonmetal in the chemical formula is sandwiched in between. For the third one, that is an oxyacid, I recognize the PO4, which is phosphate. And so remember that we're going to change the ate ending to ic. Phosphoric acid is very similar to sulfuric acid in that we have to take a little bit more than just the beginning of the name of the nonmetal. In this case, we do phosphor. Instead of phosphic, it's phosphoric acid. So how do we write a chemical formula for a binary acid? It's simple. You do it just like we've done in the past, but this time we're going to use the hydrogen ion as the cation. We'll write the anion symbol in charge, and then we'll balance the charges like we normally do by adding the appropriate subscript to the hydrogen cation, or we'll use the crisscross method. So in example 4, I notice the prefix of hydro and the suffix ic. I know this is a binary acid. I'm going to take the H+, which was representative of acid, and I'm going to find the root, which is brome. That must be the nonmetal bromine. Find its charge, which is -1, and I'm going to look to see if those 2 charges add up to 0. If they do, I'm just going to bring them together, and I have my chemical formula. It is typical to put AQ next to the chemical formula to represent aqueous. Remember, an acid is a covalent compound that is dissolved in water with a hydrogen ion as a cation. To write a chemical formula for an oxyacid, we'll do the same technique. We'll write the cation, H+. We'll then look to see if it's an ic acid or an S acid. If it ends in ic, we'll replace it with 8 and then identify the polyatomic ion, its charge. And if it ends in us, we'll replace it with ite and identify the polyatomic ion and its charge. We'll add subscripts to the hydrogen cation to balance the charges or use the crisscross method. So carbonic acid is an oxyacid. I notice the ic ending, there is no hydro. And so I know that I'm really looking at a chemical formula that has the carbonate ion. I look that up on the reference sheet. It's CO3 - 2. Since it's an acid, I'm going to put a hydrogen in front. Notice that the 2 charges do not add up to 0. So I'm going to crisscross them down, and when I rewrite the chemical formula, you'll notice that it's H2CO3. Example 6 is also an oxyacid. This time it's ending in us. So that means that the polyatomic ion is chlorite. I'm going to look up chlorite on the reference sheet, which is ClO2 - 1. Because it's an acid, I'm going to add the H+ at the front. And these 2 will add up to 0, and so I will just simply bring them together. So here's your self-check. Go ahead and try these 2. Check the answers on the next slide. All right, so this first one is an oxyacid, and we know that it's ending in us, which means it must be phosphite. The problem with this one is if you go to your periodic table, you will only find phosphate. Phosphate is PO4 - 3. Well, the difference between phosphate and phosphite is the oxygen number. Ites usually have 1 less oxygen than the 8 version. So phosphite is really PO3, and it will have the same charge of -3. So when I add the hydrogen in front of that of +1, and then do my crisscross, you'll notice that I end up getting H3PO3. The second example is a binary acid. I know that by looking at the prefix hydro and ic. That means it's going to consist of a hydrogen and whatever the nonmetal is, which is iodine. Those two charges are equal to 0, and so I just bring them together to get Hi. So if you're having trouble writing the names or the formulas for acids, make sure that you go back and you look at the two flow charts from section 2.2 and 2.3. Those should help you out. In all actuality, you only need to know 5 acids for this class, and they are on the screen that we are looking at right now. Please make sure that you know both the name and the formula. So basically, I'm asking you to memorize them. So now that we know what an acid is, what is a base? Well, Arrhenius defines a base as a substance that produces hydroxide ions in water. If we take a look at sodium hydroxide, you'll see that it's in solid form, and when it dissolves in water, it actually separates into the sodium and the hydroxide ion. And you can see that in this picture right here. The hydroxide ion is characteristic of a base and identifies a base. So how do we identify bases? Most bases in this class will be an ionic compound that has a metal paired with the hydroxide ion, as seen in the examples below. You can see here that the sodium and the hydroxide are in a 1-to-1 ratio because of their charges, and in the second example you can see that because of their charges they're in a 1-to-2 ratio. There is another type of base that you need to be comfortable in identifying, and that is the ammonia molecule. It is represented as NH3. The last thing I want to mention is that we don't want to assume that all compounds that end in OH are bases. If we take a look at this example right here, you'll see that there's an OH, yet the beginning is not a metal. It's actually a set of nonmetals. This is actually an organic compound called an alcohol. So be very careful when identifying a base. We were looking for either ammonia, which is right here, or a metal paired with hydroxide. To name and write formulas for metal hydroxides, which are bases, we're going to follow the rules for ionic compounds in section 2.2 and 2.3. Keep in mind that if we run across NH3, it is called ammonia. Notice that ammonia does not have the OH ion in it. So how is it classified as a base? Well, if we take a look at the picture below, you'll notice that when it is dissolved in water, it actually takes a hydrogen from water and leaves OH ions behind. That's what classifies ammonia as a base, is the presence of those hydroxide ions in the solution. All right, so example 7 is a base. I recognize that because I see the OH and I also see a metal. So I'm going to follow my rules. For a ternary ionic compound, I'm going to cut it before the polyatomic ion. I'm going to name the metal, which is sodium, and I'm going to name the polyatomic ion, which is hydroxide. I want you to take a few moments to do the self-check here. Notice that the first two, the formula is given to you, you need to write the name, and the latter two, the name's been given to you, so you need to write the formula. So the first two are bases, and that's because I see the OH and a metal sitting in front. So I'm going to go ahead and just cut those right before the OH, and I'll name the metal. In the first case, I've got calcium, and of course OH is hydroxide. In the second example, I have potassium, and of course OH is hydroxide. In the latter two examples, you've been given the name. We need to come up with a formula, and so what we're going to do is we're going to translate the metal name to a symbol. Remember, when you see a Roman numeral, that means it's a group 2 metal, and that is its charge. Of course, hydroxide is OH minus 1. Those two charges are not equal to 0 when added. So we're going to bring the numbers down, and that's how you get Cu parentheses, don't forget those, OH2. For lithium hydroxide, lithium is Li. There is no Roman numeral, so I'm going to look up its charge on the periodic table. Hydroxide is OH minus 1. These two charges do add up to 0, and so I'm just going to bring them together to get LiOH. So as mentioned in the beginning that there are several definitions of acids and bases. the two gentlemen of Bronsted and Lowry came up with a secondary definition for an acid, and they defined it as a substance that is a proton or hydrogen donor. So in this kind of example, the first thing that I want you guys to do is take a look at the left side and the right side of the equation, and I want you to make connections between the substances that look very similar to one another. Notice that the HCl has become Cl. What that means is it has lost or given up or donated a hydrogen ion, and thus it's classified as an acid. So Bronsted and Lowry also identified a base as a substance that is a proton or hydrogen acceptor. If we do the same thing we did a few minutes ago by connecting the substances that look similar to each other, if we look at NH3 and how it's changed to NH4+, you will notice that it accepted a hydrogen ion. And so that's why it's called a base. Now, where did it accept that hydrogen ion from? Well, it accepted it from the hydrogen. And as the hydrogen donated its hydrogen ion to NH3, it became OH-. And that's why H2O in this grouping is also considered an acid. So Bronsted and Lowry realized in this process that acids and bases can create conjugate acids and bases. They will be found on the right side of the equation. Before we can get to that, let's do a quick review on what an acid and a base look like in this form. We're going to go ahead and pair up the similar species, and we'll notice that HNO3 becomes NO3-. Notice that it has lost a hydrogen, and thus it's going to be considered an acid. H2O has become H3O. It has accepted a hydrogen, and so it will be considered the base. If we take a look at the second example and we connect any of the substances that look similar, we will find the same thing happening. Ammonia becomes the ammonium ion. It has gained a hydrogen, and thus it's a base. Water has turned into the hydroxide ion. It has lost a hydrogen ion, and thus it is considered an acid. Now, in order to identify the conjugates, we're going to actually look at this reaction in the reverse direction. So if I do the same thing I just did a few minutes ago, connect the pieces that look similar. If I look at NO3-, you will notice it becomes HNO3. This time the NO3- has accepted a hydrogen ion, so it is going to be considered a base, and because it's on the right side, it is a conjugate base. If we take a look at the hydronium ion, it becomes the water molecule. It has lost a hydrogen ion, and so this is the reason why it will be considered a conjugate acid. In example B, if I pair up the similar species and do the same thing, if I go in the reverse direction, you'll notice that the hydroxide ion becomes water. It has gained a hydrogen ion, so it's a conjugate base, and the ammonium ion becomes the ammonia molecule. It has lost a hydrogen ion, and it is considered a conjugate acid.